Yeah, I think we have everybody from the waiting room, so we can start. So good afternoon, everybody, or good morning or good evening, wherever you are. Welcome to this online event. My name is Eric Loga. I'm one of the co-lead editors of Physical Review Fluids, the other being Beverly McEwen from Caltech, who's in the audience. It's my pleasure to welcome you to our second Physical Review Fluids Journal Club from APS. I would like to ask you to please mute yourself and also perhaps turn off your cameras during the talk. Today's session will be moderated by Michael Brenner from Harvard University, who's an associate editor of Physical Review Fluids. So I'm going to leave the floor to him, and I hope you will enjoy the event. Michael.
Okay, so thanks everybody for coming. We're really excited about this session that is going to highlight a paper that Juliette Pierre wrote with her colleagues on the sound of effervescence. That is the mechanisms behind the sound when a bubble pops at a liquid interface. And what we're going to do is I'm going to turn it over to Juliette, who's going to talk about the work for about 15 minutes, and then we will have 15 minutes of questions. So just to be organized, I guess what I would request is that if you have a question, if you could put it in the chat, and I will then go through it after Juliette is done with her presentation, and maybe we'll also open it up to people to ask questions directly as well. But I guess that's it. So with that, Juliette, do you want to take it from here?
Yeah, it's okay.
Yeah, that looks great.
Okay, thank you. Good morning, good afternoon, good evening, everyone. This work has been realized during the PhD of Mathis Pujol and in collaboration with Régis Burger, François Olivier, and Arnaud Enkoviak, everyone from Danube Institute in Paris. So for the first experiment I want to show you, I need a glass of champagne, one high-speed camera to look at the top of the glass, and one microphone synchronized with the camera. So, sorry. You will see a short movie of 1 second, slowed down 10 times. So you will see here the top of the glass. You will hear the fizzing sound of the glass, and you will see what you will hear on this plot showing the temporal evolution of the acoustic pressure recorded above the glass. So, the bubbles are created on the wall of the glass. They rise and settle on the surface and finally burst. And during this time, the microphone records a succession of tone bursts. And if we zoom around one single tone burst and compare it with images, the comparison reveals that this tone burst seems emitted concomitantly with one single bursting bubble. Now, if we look at the frequency signature of this single event, it looks very similar to the spectrum of the hundred of tone bursts recorded during 1 second. So these two observations suggest that the crackling sound of a glass of champagne results from a superposition of tone bursts emitted by single bursting bubbles. So, okay, but what is the physical mechanism behind that? What does the literature say us about that? In 1992, Donald Speed realized an experiment on single bubbles bursting at the surface of a water bath, and he interpreted the sound as a transient acoustic emission associated with the oscillations of Helmholtz resonator following the instantaneous release of the initial overpressure contained inside the bubble. And the central frequency of the oscillation quantitatively agree with Helmholtz resonator model, which depends on the sound velocity and the geometry of the bubble. I will come back on this model in few slides. And Spiel also observed that the frequency of the signal emitted by bubbles smaller than 1 millimeter increases in time. And according to this work and the more recent work of Dean, the film retraction and the volume collapse, the collapse of the cavity, were speculated to play a role. But they are just speculation because they don't watch the bubble during the sound recording. So in this paper, we wanted to clarify this question. And to do so, we built a well-controlled experimental setup with 2 high-speed cameras synchronized with a microphone. So bubbles of air with a radii between 0.3 and 3 millimeter are generated in a water tank using capillary needles with various interior diameter. So the bubble is detached from the needle, goes to the surface, and remain enough longer to be at the hydrostatic equilibrium. And finally, the bubble bursts following several interfacial reconfiguration, as you can see here on this movie. And so one camera records the collapse of the submerged cavity, and the other look at the surface. So before bursting, if we come back a little bit like that, so before bursting, the bubble is at the hydrostatic equilibrium and overpressurized at Laplace pressure. So the bubble is closed by a thin liquid film, which becomes thinner and thinner by drainage until burst. And at this stage, the overpressure is released in the air, and the submerged cavity become out of equilibrium. So capillary waves are generated, they propagate at the liquid-gas interfaces and converge at the bottom of the cavity, leading to cavity reversal. And finally, a fast and thin jet is ejected in the air. So basically, the complete bursting occurs at different time and length scale, from the microsecond to the millisecond, and from micrometer to millimeter. And if we look now at the synchronization between images and acoustic emission, as you can see on this acquisition for 1 millimeter bubble, the acoustic emission starts when the cavity opens and finishes when the cavity starts to collapse. So we record no acoustic signal during the collapse of the submerged cavity and also during the jet propagation. And also, if you look carefully on this temporal signal, you can see that the frequency seems slightly increases in time. And this is confirmed by this spectrogram, representing the frequency as a function of the time. And here, I superimpose with black dots the central instantaneous frequency. And this is what we get for several bubble size. So on this graph, I represent the instantaneous central frequency as a function of the time for 3 different bubble size. And what observation can we make on this graph? First, the frequency decreases with the bubble size. Then the frequency for each bubble, the frequency increases with time. And also for each bubbles, we observe 2 acoustical regimes. And in the first one, the frequency agree with the square root of the time up to a certain time called tau b. And after this time, the frequency becomes quite constant. So during this time, what happens for our bubbles? Right? Yep. It's working. So as I said before, the submerged cavity remained quite the same during the whole acoustic emission. So then we can focus on the aperture of the bubble. So when the bubble rises the surface, it equilibrates. Then the thin films open from nucleation point, when the film is fully open, fully broken, the cavity edge starts to retract. This is what you can see on this movie. Slowed down 2,000 times. So the dynamics of the film dynamics aperture and the rim retraction are completely different. And on this graph, I represent the size of the cavity aperture as a function of the time for 3 different bubbles. And the first the film retraction is driven by the well-known Taylor-Kunig velocity, depending on the surface tension, the density, the liquid density, and the thickness of the film. And so one goes from this constant velocity when the film opens, around 10 meters per second, and to another velocity, much more slowly, around 1 meter per second, when the rim retracts. So this behavior looks very similar to the one of the temporal frequency shift that I show you at the present slide. And this is confirmed by this graph when where I represent the time of transition for the frequency as a function of the film, the time of the film opening. And they both coincide very well for bubbles larger than 0.5 millimeter. So we thus expect a relationship between the acoustic emission and the film aperture. So to interpret that precisely, what the acoustic says. If you blow in a bottle, you can hear a sound at one precise frequency. This is the resonant frequency, so-called Helmholtz resonance. And it is a signature of an open cavity behaving as a mass spring harmonic oscillator. And in this case, inertia is due to the mass of air contained in the neck, and the stiffness is associated to the compressibility of the large volume of air contained inside the cavity. And the resonant frequency depends on the gas sound velocity and the geometry of the system. And also on a small, depend on a small correction equal to the dimensionless parameter epsilon times the radius of the aperture. And this correction reducing the influence of the air flow inside and outside of the aperture. In the case of an open sphere, like our bubbles, there is no neck, and the oscillating volume of air is delimited by the section of the aperture and a small length defined by epsilon times the radius of the aperture. Now the frequency resonance depends on the sound velocity in the gas and two geometrical parameters, the radius of the aperture and the bubble radius. But it is not so simple for our bubbles, because in the case of the bubbles, the radius of the aperture, the orifice, increases in time. So we build a model considering two limits. In the first one, the film retracts, and in the second one, so this is the first one, and the second one, where the film is fully broken. And in this case, we considered that the frequency value when the film no longer exists is an asymptotic value, sorry. So we did it because we have, as I said before, the velocity of the ring retraction is slow and the cavity volume remains quite the same during the whole acoustic emission. So as a first comparison, we superimpose on the previous spectrogram these two theoretical expressions. And it's worked quite well. So now to check the robustness of this model, we can look at the two parameters for various bubble size. The first one is the prefactor beta, the prefactor of the time beta in the first regime. And the second one is just the frequency resonance when the film is fully broken. And so first, one can observe that the beautiful coincidence between the theoretical beta and the experimental one, the expected one. I forgot to tell you that for both graphs, we represent the two extremum conditions for the dimensionless parameter epsilon. It is close to 1, but for the accuracy, I represent both. So when the field is fully broken now, the expression of the resonant frequency is more simple, and it depends only on the gas properties with the velocity and the liquid properties with the capillary length, and it depends only on one geometrical parameter, the bubble radius. And here again, as you can see here, the theory and the experiment are in very good agreement. So our lumped element model works very well quite well for isolated capillary bubbles. At this stage, everything seems to be well understood. But if we look at the quality factor of this resonance, it is interesting to observe that it doesn't depend on the bubble size. And we don't know why. Because for a resonator with a negligible neck, and under the assumption that there is a negligible thermoviscous dissipation, we expect this relation. We expect that the quality factor decrease with the bubble radius. And clearly this relation doesn't agree our experiment, especially for small bubble. So in fact, we believe that the thermoviscous dissipation occurring in the vicinity of the neck may explain the observed discrepancy, but this remains an open question at this stage. And before conclude, I want to come back quickly on our sparkling wine, and using the image, I can extract the bubble size distribution at the surface of the glass. And so the question is, if I consider that the emitted sound of the fizziness comes from bubble bursting at the surface of the wine, what is the expected acoustic spectrum for this bubble size distribution? So we work with champagne, so we need to take into account for the surface tension of the white wine, and also for the sound velocity in the gas trapped inside the bubbles. And we use the closed form of the Helmholtz resonance. And in this case, we neglect, by simplicity, we neglect the first regime characterized by a frequency, by the frequency chirped, but we hope to catch the main part of the spectrum doing that. And the coincidence between the Helmholtz model here in green and the frequency recorded by the microphone in black, at the end, it's great. It's worked very well. And actually, there is another source of sound, possible source of sound, the monopolar resonance of the bubble inside the liquid, so-called Minard resonance. And indeed, for example, for the rain noise on the sea, the rain noise of the sea is explained by the sound produced by small bubbles entrapped during the collapse of the cavity formed after the drop impact. But as you can see, the coincidence with our measurements is not great at all in this case. So finally, it is interesting to note that the main part of the acoustic emission is in the ultrasonic regime. Thus, we hear just a small part of the spectrum. And so the sound of effervescence comes from the early time of the death of the bubble, when the film just starts to break. So bursting bubble can be seen as Helmholtz resonator. When the Laplace of a pressure is released, the frequency of the resonator increases with the film opening. And we also, this is a well understood question, but we also identify two open questions, which can be important, for example, for acoustic monitor, if we want to do acoustic monitoring for such fast hydrodynamics events. So how can we explain the measured quality factor? And I didn't have time to talk about it, but how to evaluate the dissipated energy. So thank you for your attention.
Okay, great. Thanks, Juliette. That was a wonderful, the work is beautiful, and it was a wonderful presentation. So now people should feel free to ask questions in the chat. So there was one question already, and actually it's complementary to a question that I had and something you just alluded to. So Roberto Zenit said, the sound produced by the bursting bubble is not influenced by the fact that the liquid is champagne. Is that correct? So that was his question. And sort of the comment I wanted to make is that, you know, there's another phenomenon that that also produces sound from bursting bubbles, but which occurs in a much more viscous limit than the one that you're considering, which is if you ever make sugar water, if you make caramel. So what happens when you make caramel, if you heat up sugar water, if you boil it, as the water evaporates, the boiling temperature of the mixture goes up and the thing makes sounds. There's a sound that occurs. And in fact, chefs can tell the temperature of the mixture to extremely high accuracy by just listening to the sound. And it seems like it's probably the same phenomenon that you're describing here, but it's in the viscous limit where dissipation would play a role.
Yeah, and in viscous liquids, we can also expect to hear the sound of small bubble as entrapped in the liquid when the cavity collapse, like in for the raindrop. Small when the cavity collapse, there is a small bubble. A small bubble can be entrapped in the liquid, and for viscous liquids, this is not the case in for champagne, but in very viscous liquids, for capillary bubbles, you can have small bubbles entrapped in the liquid, and this bubble can make a strong sound. And for boiling liquids and viscous boiling liquids, I think these two source of sound can be explored.
But I guess that the experimental setup that you built will beautifully work when you increase the viscosity of the liquid too. So this should be something that you can investigate.
Yeah, of course. I want to do this and to look at the transition with bigger bubbles for example, to explore the sound produced by a mud.
Yeah, when you say bigger, you mean when the bubble size is of order of the capillary.
For the bubble size for volcano muds, for example.
Yeah,
because it's a shift in frequency scale change.
Yeah, no, that sounds good. It's really a beautiful experimental setup. I can keep asking questions, but do other people have questions? Oh, Bruce asked a question. Okay, so Bruce Sutherland says, is it reasonable to assume that your results extend to a bubble bursting with adjacent bubbles or a bubble against a glass side wall?
Yes, I see the question. In fact, it was our first assumption that recording the sound above the glass of champagne, we hear a difference of in the signal, but at the moment we don't hear difference. But we have to build an experimental controlled, well-controlled experimental setup to generate a lot of bubbles with the same diameter to control the experimental setup, and we want to do
right. But I mean, in principle, given the separation of scales, you seem to have captured the dominant effect in champagne, and that the plot you showed at the beginning with the single bubble compared with the bulk was pretty convincing, I thought.
Maybe if there is two slice or two level of bubbles, maybe you can have an effect on that. But,
can I ask another question? Could you go back a slide to the one with the miniart frequency on it? Could you go? This slide. So actually, so what's interesting is that this comparison with the miniart model. It's true. While it's true that quantitatively the frequencies are off, in the low frequency limit, both the experiments and the miniart model predict that the frequency should increase dramatically. That is, the shapes of the curves look kind of similar. I wondered if you could comment on that in the low frequency limit. That part is going up.
I think that it just it's come from the microphone. It's not a signal.
I see, that's from a microphone.
I don't. We choose to don't cut this frequency, but to compare very well with this bar. But for me, it's not a signal.
That makes sense. That totally makes sense.
Yeah.
Cool. Good. Okay, so Howard Stone asked a question. He says, would you expect any change for a carbonated beverage? Could you see the effect of the gas with this?
We take into account for the gas velocity in this case, and we try to do measurement with perfluorohexane. We put perfluorohexane inside the bubbles, because perfluorohexane is the velocity inside for this gas is 5 times less. No, the density is 5 times less than the air. So no, 5 times more. It's heavy. Yep. So it's very different for the perfluorohexane. So we try to do experiment with this gas, and it changed the frequency, but it's very hard to. It's tricky to have a well-controlled experiment because the outside of the bubble it is air. So when the bubbles open, we don't know the dynamic of the gas exchange in between the cavity and the air. So
Michael, can I just add?
Yeah, please.
I was just thinking of an undergraduate lab that you could drink, and obviously Coca-Cola might be better than an alcoholic beverage for students. That was sort of the nature of my thinking about an undergraduate activity or high school.
We try with sparkling water.
Or a high school activity even.
Yeah, we do that with sparkling water.
It's healthier than Coca-Cola.
Yeah.
Good, thanks. Are there other questions that anyone has for Juliette? This is really beautiful work, Juliette, and I guess we look forward to seeing the future studies that you produce with this experimental apparatus, which just seems so interesting. Does anybody have other questions, suggestions for Juliette? What would you do if you had this amazing experimental apparatus? Good. Kishore Dutta says, would you suggest any dynamic model that can possibly explain the emerging phenomena, at least to some extent? I'm not sure I understand. Kishore, could you tell us, what do you mean by the emerging phenomena?
Yeah.
If you're there, you can speak.
Yeah, I don't understand the emerging phenomena.
Yeah, okay. Yeah, I don't.
Sorry.
Yeah, I don't understand. Other questions or comments? So if not, I think we should all thank Juliette. That was wonderful, Juliette. It was really nice. That was a beautiful presentation. And also let's thank Eric and Beverly and Brad for starting this wonderful series where we can all learn about fluid mechanics in either the morning or the afternoon, wherever we happen to be. So
thank you very much.
Thank you, everybody, for coming.
Thanks, everybody.